Last time we drew a caricature of the intermediate state proposed to close the gap between molecular deuterium and the helium-4 fusion product. We pointed out the parabolic potential the electron feels moving away from the z-axis. Here we sketch in the resulting Gaussian wave function. This would represent the electron wave function along a line in the x direction through the center. We also showed a calculated wave function for the electron along the z-axis, and we also sketched that in here. The overall wave function for the two deuterons and electron is given by multiplying the three independent wave functions for the electron times the overall wave function for the deuterons. It's interesting to watch the change of the electron's z-axis probability as the deuteron approach each other. The electron kinetic energy for the given separation is also displayed on the graph. The electron energy as a function of deuteron separation can then be drawn as in this graph. We can add the deuteron Coulomb repulsion energy plus the sum of the two as in the following graph. This is reminiscent of the potential we drew for the molecular ion and redraw here. We want to focus for a moment on the minimum created in the potential for the molecular deuterium. We can draw the wave functions for the different energy levels roughly as shown. Each successively higher energy level has one more hump on the curve. We can then do the same thing for the deuterium intermediate. We draw in only the very highest energy level with n equal 35 or 35 humps. We'll find out later that this highest energy level is the only possible state for quantum mechanical reasons we will explain later. Now that we have wave functions for our molecular D2 and the intermediate D2 star, we can think about the transition between them. Recall that the molecular D2 orbits leading to probability distributions looking something like this. We can add the intermediate state and get a picture looking something like this. It's fairly obvious from the sketch that the transition from molecular D2 to the intermediate will be slower than the fusion transition D2 star to helium-4. Next time, we will discuss two-state time dependency from the quantum mechanical point of view and apply this to our two transitions. We know there are many doubts and questions and don't want to lose people due to cognitive dissidence, so a couple of intuitive clarifications. First, the apparent uncertainty contradiction. Recall our D2 star cartoon. We can draw in the Gaussian probability at a few points along the z-axis and point out the approximate calculated widths. Note at the nuclei the electron stays within the deuteron diameter. This, of course, shows what a cartoon the sketch is. Since drawn to scale, it would look more like this. Sketching in the z-axis probability shows that the electron is mostly quite near either deuteron. This presents a quandary as the electron orbits with the deuteron with the same velocity. Because the electron is about 4,000 times lighter, this will give a wavelength much too long to fit in the orbit, as depicted in this sketch we've used before. But recall the electron orbits the z-axis also with very high velocity, and this tangential velocity is applied to create the proper wavelength as shown in the sketch. Thus, no contradiction to the uncertainty principle. Another question that we struggled with is the notion that the electron drops into a potential well when it doesn't lose energy. This is easiest to comprehend if we keep in mind this is a diffraction pattern for the electron, and so can be thought of as transitory. This simple example shows how a ball can roll by a potential different ways. It can speed through the center or get caught circling before it leaves, thus spending more time in the potential well. This happens because temporarily kinetic and potential energy is shared with another dimension.